By the way, yeah, so here, of course, after we simplified, there were only y's here. There were no x's. And that's kind of good news. I mean, if you had an x here in this expression, that would have told you that something is going wrong. Right? G is a function of y only. So if you get an x here, maybe you want to go back and check whether it is really a gradient field. Yes? Yes, this will work with functions of more than 2 variables. So both methods work with more than 2 variables. So we're going to see it in the case where more than 2 means 3. We're going to see that in 2 or 3 weeks from now. I mean, basically, starting at the end of next week, we're going to do triple integrals, line integrals in space, and so on. So the format is first we do everything in 2 variables, so then we'll do it in 3 variables, and what happens with more than 3 will be left to your imagination. Okay, any other questions about either of these methods? Okay, a quick poll. Who prefers the first method? Who prefers the second method? Wow. Okay. So, well, anyway, I mean, you get to use whichever one you want. And I would agree with you that the second method is slightly more effective in that you're writing less stuff. You don't have to, set up all these line integrals for nothing. On the other hand, it does require a little bit more of attention. Okay. So, well, let's move on a bit. Well, let me start by actually doing a small recap. So we said we have various notions. One is to say that a vector field is a gradient in a certain region of a plane. And we have another notion which is being conservative, which says that the integral, the line integral is 0 along any closed curve. So actually, let me introduce a new piece of notation. So to remind ourselves that we're doing it along a closed curve, very often we put just a circle through the integral to tell us, well, this is a curve that closes on itself. It ends where it started. I mean, it doesn't change anything concerning the definition or how you compute it or anything. It just reminds you that you're doing it on a closed curve. It's actually useful for various physical applications, and also, when you state theorems in that way, it reminds you, oh, I need to be on a closed curve to do it. And so we've said these two things are equivalent. And now we have a third thing, which is n sub x equals m sub y at every point. So just to summarize the discussion, we've said if we have a gradient field, then we have this. And the converse is true in suitable regions. So we have the converse if f is defined in the entire plane. Or, as we'll see soon, in a simply connected region. Okay, I guess some of you can't see what I'm writing here, but it doesn't matter because you're not officially supposed to know it yet. That will be next week. Okay, anyway, so I said the fact that nx equals my implies we have a gradient field is only if the vector field is defined in the entire plane or in a region that's called simply connected. And more about that later. So now let me just introduce a quantity that probably a lot of you have heard about in physics, that measures precisely failure to be conservative. So that's called the curl of a vector field. Okay, so for definition, we say that the curl of F is the quantity n sub x minus m sub y. Okay, so it's just repackaging the information we had, but in a way that's a single quantity. Okay, so in this new language, the conditions that we have, the condition that we had over there, this condition says curl F equals 0. That's the new version of nx equals my. Okay, so it measures failure of a vector field to be conservative. So I should probably so the test for conservativeness is that the curl of F should be 0. So I should probably tell you a little bit about what the curl is, what it measures, what it does, because that's something that's probably useful. It's a very strange quantity, right, if you put it in that form. I mean, yes?
Is this one the same as the physics one, or is this the opposite?
I think it's the same as the physics one. But I haven't checked the physics textbook recently, but I believe it's the same. Yes, I think it's the same as the physics one. It's not the opposite this time. Of course, in physics, maybe you've seen actually curl in space, and we're going to see curl in space in 2 or 3 weeks. But yes?
So do you only use this test if the function is defined at every point?
Yes. Well, you can also use it. So if you fail this test, then you know for sure that you're not a gradient field. So you might as well do that. If you satisfy the test, but you're not defined everywhere, then there's still a bit of ambiguity. And you don't know for sure. Okay. Okay, so let's try to see a little bit what the curl measures.